Welcome to the lectures on modern digital communication techniques. So in the previous few lectures, we have been looking at the situation where channel is no longer AWGN, but it is finite band limited, and we did discuss the maximum rate of signaling under such conditions. Then we discussed the concept of Nyquist filter, and we further stated that it is not realizable, and hence we tried to investigate if there are other ways of realizing such a filter. So what we found is that to signal at 2 times the Nyquist rate, you need to have an excess bandwidth, which is the design trade-off. After discussing these details, what we tried to do is if it was possible to restrict the signal within the Nyquist bandwidth, and yet we could communicate at 2 times the Nyquist bandwidth. And we found that it is possible to do so if we could use some kind of a signaling known as partial response signaling, and we did give examples of duobinary signalings. In such a method, we found that since the signal stretches more than the symbol period t, in other words, because the pulse duration is longer, the bandwidth is less, it introduces inter-symbol interference. So we brought in the concept of controlled inter-symbol interference. Because of controlled inter-symbol interference, we could recover the signal by virtue of subtracting the interference caused. We did so by recalling that the previous time sample or the previous time instant, we could decode the symbol of interest. We moved further and we discussed 2 kinds of such pulse shapes. One is the duobinary, one is the modified duobinary, and we also stated that instead of cancelling the interference at the receiver, one could do it at the transmitter. Meanwhile, we did discuss the effect of noise and the issue of error propagation. So we further discussed that we could do pre-code, that means at the transmitter we could do a duobinary, we could do a modulo 2 subtraction, by which we would get a binary sequence which would be used for modulating a binary PAM. After discussing the pre-coded scheme, we moved forward to discuss the Emery PAM with such kind of signaling, and we did give the expressions of how the things would work out to be, and examples would be shared in the assignments and tutorials. After looking at such signaling methods, we turned our attention towards non-ideal channel. In non-ideal channel, we found that an impulse launched into the channel produces a response which is no longer an impulse, but is a spreaded version of the impulse. Now, since the output of the channel has echoes and it extends beyond the impulse, therefore, a sequence of symbols launched into the channel would cause inter-symbol interference. And we did discuss that the overall system transfer function requires to be a raised cosine in order to make things realizable as well as inter-symbol interference free. We stated that if the channel is unknown, which is generally the case, then the transmit filter and the receive filter are designed in such a way that when in cascade they form the raised cosine. Accordingly, each one of them are root raised cosine. So we are left with the channel as well as the equalizer. So if the channel transfer function multiplied by the equalizer transfer function produces unity, we would get the cascaded transfer function of the transmit filter, the channel, the receive filter, the equalizer as raised cosine, which would result in an ISI free communication. So that results in finding or taking the equalizer coefficients as inverse of the channel transfer function. What we did see in that is if you do it in such a way, wherever the channel transfer function takes small values, 1 upon channel transfer function would take very large values. And when this factor gets multiplied with the noise, we get noise enhancement. Noise enhancement decreases the performance of communication systems. To overcome that, we suggested the use of the minimum mean squared error criteria based equalizer. The equalizer looked complicated, but we could break down the equalizer with certain approximations and assumptions or with certain relaxation, and we found under certain special cases it turns out to be equal to 0 forcing, or in other words we also stated that the MMS equalizer restricts the enhancement of noise by including an additional parameter along with the inversion of the channel coefficients. So, it does not allow the magnitude to grow very large, it limits the amplitude growth by 1 upon SNR. So, after discussing the 0 forcing and MMS equalizer, we also discussed the possibility of including an adaptive equalizer. That means, instead of waiting for a long duration, you can continuously adapt the tap parameters. To study that, we presented two models. One was the system identification model, in which case we would identify the channel parameters. Once we identify the channel parameters, you could use it to equalize the channels. The second model we presented was of inverse system identification. In the inverse system identification, one would directly estimate the equalizer coefficients so that the signal out of the equalizer would match the desired signal. We also briefly stated that to estimate these parameters, one should send an impulse in order to get an impulse response or find the inverse impulse response. But since sending an impulse would cause an unrealizable transmission design, we stated that PN sequence is generally preferred, whose transfer function would have uniform gain across the desired set of frequencies. We also stated that it is very important to design training sequences carefully, because the synchronization which we are about to start would depend on such techniques. After discussing channel equalization methods, where of course we included the method of steepest descent as well as stochastic gradient algorithm, where we briefly stated the outcome and we said that you can find out the details of it in other detailed subject, whereas in this course we are interested only in the final expression, because we are using those results in the equalizer. And again, just a reminder, these sections are a little bit advanced. So, from the examination point of view of this particular course, we will be considering the time constraint that you have in answering such questions. However, I would like to highly encourage you in pursuing those aspects if you are really interested in implementing a state of the art receiver. So, when we move on to study the parameter estimation such as carrier frequency synchronization and timing synchronization, we need to resort to certain theories known as the estimation theory and detection theory. Unknowingly, we have explained to you some aspects of those theory which we will repeat at certain points. So, let us quickly brush through some of the things which we discussed in the previous lecture, so that we can use them effectively in designing algorithms for carrier synchronization and timing synchronization. So, we studied the signal parameter estimation problem. In the signal parameter estimation problem, we stated it as a mathematical statement, and we said that since the data is inherently random, we use PDF to describe the data. And we also stated that in determining good estimators, the first step is to mathematically model the data. Typically, the PDF is parameterized by unknown parameter of, let us say, theta, and we briefly explained with this diagram. Hope this will remind you of what we discussed. So, we did bring in the concept of likelihood function. So, this is if x0 is observed at certain point, let us say x0 is observed here, we said that if x0 is observed here, if we go up along this curve and go to this y axis, we will find the likelihood of observing x using this function, right, which is parameterized by, let us say, the mean theta. So, what we stated is that the parameter has caused the occurrence of x, and now since we have observed x, we want to infer what was the cause which has produced this x. So, with this we also discussed certain other important things, like when we estimate the parameter, how close will the estimate be to the actual parameter, and are there better estimators. So, while discussing this, we did talk about the minimum variance unbiased estimator, where we said an estimator is unbiased if on an average it meets the value, and its minimum variance if there are no other estimator whose variance is lower than the current estimator. And we discussed the Cramer-Rao lower bound. The Cramer-Rao lower bound tells that if we, I will go to that. So, this picture that we looked at briefly tried to explain the likelihood function and the importance of variance with respect to the likelihood function. A smaller variance means dependence of the unknown parameter on the PDF even more. So, we moved further and we discussed the Cramer-Rao lower bound, in which we stated that if the regularity condition is satisfied, which has the PDF. So, we have modeled the data, we have the PDF of the data, we have assumed a PDF, we did have a short discourse on assuming the PDF. So, if this condition is satisfied, then Cramer-Rao lower bound gives a bound on any estimator that may be found, a lower bound on the variance of the estimator, right. So, any estimator cannot have a variance which is lower than this, that is what it stated. It also stated that if we are able to factorize the first derivative of the log of Px, which we have written it better over here, that if we are able to factorize the log likelihood function, the derivative of the log likelihood function into this form, then Gx would form the efficient estimator. That means, it would estimate theta without any bias, as well as the variance would be minimum, right, and the variance is given by 1 upon I theta, where I theta is given by this term. So, the advantage of using the Cramer-Rao lower bound is that if you can find the first derivative of the log likelihood function and you can factorize in the form as discussed, then you will find the efficient estimator directly without much of a problem. However, the problem is we do not always get the opportunity to solve that particular equation in terms of factorizing the first derivative of log likelihood function, and then we are stranded and we do not know how to find a good estimator. So, to our rescue, we have the famous expression or the method which we have already used is the maximum likelihood estimator. So, since we have already used the maximum likelihood estimator, the discussion in this part will almost be pretty easy, and it will remind us about the things that we did before. So, here we formally have the maximum likelihood estimator with us. So, in some situations the MVU, that means the minimum variance unbiased estimator, either it does not exist or it cannot be found, right. It can happen in this situation. So, in those cases you would like to use the maximum likelihood estimator, and we have already done this thing, and it is very popular. It is a very popular estimator and generally used for practical purpose. So, you can almost go ahead and start by using the maximum likelihood estimator, but just to remind you that when you are using the maximum likelihood estimator, that means you have already made some assumptions, and one of the strong assumptions is that you already have the likelihood function with you. So, if you do not have the likelihood function, in that case you cannot use the maximum likelihood estimator, because it depends upon the likelihood function. In those cases, even this is not usable, and we would resort to solutions such as the least square solution, which gives us the zero forcing algorithm, or the minimum mean squared algorithm as we have presented before. So, this particular estimator is optimal for large data records, and it approximately or asymptotically it is the MVU estimator. We will talk more about this. The maximum likelihood estimator is obtained using the maximum likelihood principle. We have already done this, and for a very large data set, n means the number of observations, as n tends to infinity, the expected value matches the data set, the actual data to be estimated, and as n tends to infinity, the variance of the estimator tends towards the Cramer-Rao lower bound. So, that means it is asymptotically unbiased and it is asymptotically efficient. So, that means if n is very large, then it will yield asymptotically MVU. That is the advantage of a maximum likelihood estimator. And the other important part is that if an efficient estimator exists, the MLE will yield the efficient estimator. So, this is another very important part. So, this results tell us that if we have the likelihood function, we can almost go for the MLE method, right. So, we will use the MLE method for signal parameter estimation. So, the another important parameter is that the estimated parameter is generally normally distributed with a mean of whatever we have said and variance as the lower bound asymptotically, right. Okay. One of the issues with which one may concerned with is how large n is, and in many cases it is manageable. So, that is what we should remember, that in quite few cases it is doable. So, the first thing that we will discuss is, since we have already studied the MLE, and just to remind you that we have already used the maximum likelihood estimator. So, in case of the signal detection, we have used the maximum likelihood principle in finding out which particular signal has been sent, right. The MAP criteria uses the likelihood function. The maximum likelihood, we use the maximum likelihood principle when we said equiprobable transmitted signals, right. So, we had the MAP detector and the ML detector. So, we use the maximum likelihood philosophy, which states you use the likelihood function, maximize the metrics, and you have your results. So, the first example that we will take in this case now is the maximum likelihood estimator of the sinusoidal phase. So, we have a discrete signal model, x n is equal to a cos 2 pi f 0 n plus phi plus w n. So, there is noise and there is the modulated signal, there is the carrier signal with some f naught. F naught is the normalized frequency, and we will assume that we will know the amplitude as well as the frequency, and we are interested in finding the phase. W is white Gaussian noise with variance sigma squared n. In our model, it is n naught by 2. So, now we take a look at the likelihood function. So, we would generally represent with capital lambda as the likelihood function. So, it is nothing but the PDF where we have fed the value of x. So, if you look at this expression, we have white Gaussian noise. So, this is the mean of the signal where everything is known except this parameter, right. So, this will this conditioned on this is the mean, and then if we have x like x1, x2, x3, x4 up to xn, then the joint distribution would be the product of the individual or the marginal distribution, because we have white Gaussian noise, which would lead to the independence of the observed data. So, the likelihood function of x underscore indicating a vector parameters by phi is this expression which you are pretty familiar with, xn minus the mean squared and the summation, because you have a product of the PDFs. So, the summation comes, we have seen this, and there is a raised to the power of n because there are n such observed data. So, instead of taking this whole function, since we have to estimate phi, phi is available only here. Since phi is available only here, we can focus only on this part, and maximizing this means you minimize the argument, because if a smaller value in the argument would be maximization of the likelihood function. So, you focus on this metric, which would remind us about the distance metric as we had done before. So, if you take the derivative of the cost function which is in the argument and take with respect to phi, because you are maximizing with respect to phi, and set it to 0. So, if you look at this, you are going to get the expression, because there is a cos squared term, you are going to get xn squared, a squared, cos squared and 2a cos. So, from all those terms you are going to get an expression which appears here, where for brevity I have marked this as alpha n, 2 pi f naught n plus phi as alpha n. Because of shortage of space, I have used alpha n over here. And now this term would turn out to be a sine twice alpha n, right. And if you are taking the summation for f 0 not close to 0 or f naught, that means not close to the extreme values of frequency, this summation would turn out to be approximately 0. So, we are making an approximation over here that for large n and f naught not close to 0 or half, f naught not close to 0 or half, we would get the right hand side of this expansion to be almost equal to 0. So, then we can say that the left hand side is equal to 0, and now you have a sign of a plus b, I will term this as a plus b, which you will expand, and there will be, you will get the trigonometric expansion of this, and you are going to split the terms on both sides of the equality, and you will be landing up with an expression as in here, where you have a cos phi term, a sin phi term, which are the estimates, and the sin 2 pi f naught n and cos 2 pi f naught n and x n. X n is the observed data, and this is the parameter to be estimated. So, from this one can solve as the estimate of phi as tan inverse, because this is outside the summation. So, you can clearly bring it down, and tan inverse of sine of this fraction summation x n sin 2 pi f naught n upon x n cos 2 pi f naught n. Some of the few important things to observe is that we wanted to estimate this phase using the MLE, and we use the log likelihood function. From the likelihood function, we took the cost function. You could have set the derivative of this to 0, and you could have also got the same result, but we focused mainly on here, and by making another approximation where this summation tends to 0, we have come to the expression of the estimate of phi, which is the tan inverse of the observed data multiplied by sin 2 pi f naught n upon the ratio of tan inverse of the observed data times cos 2 pi f naught n. So, what it tells is that if I observe x n, I am going to multiply, I am going to get x n, right. So, I have to split x n into two parts. In one part I will multiply cos 2 pi f naught n, look at that, f naught is known for us, right, and in this part I am going to multiply sin 2 pi f naught n, right, n is the index, and then I can take the summation, I will take the summation and I will feed to a device which will take, if this is A, this is B, tan inverse of B upon A, right. So, this is going to give me the phase. So, that means using the maximum likelihood estimator, we can directly calculate the phase of the unknown signal, and of course, one could find what kind of a behavior does it have, and so on and so forth. So, why such thing is important, that why do we need to find the phase of the sinusoid carrier in this kind of a situation, is something which we should see in the next lecture. So, at least one important thing that we could conclude is that using the MLE, we could directly arrive at the estimator of phi, which is otherwise not clearly available from this expression, right. Because if you would like to estimate phi by solving algebraic methodology, you would say x n minus w n, right, divided by a cos inverse of that, and then take away 2 pi f naught n. Now, we do not have this noise, so you cannot use such a model. So, you have to use certain methodology over here, and since this can be modeled as Gaussian PDF, so it helped us in reaching this particular estimate of phi. So, we continue with the discussion on why this estimation of the carrier phase is important in the next lecture, and then we will proceed on to find the total carrier phase or the carrier frequency at the receiver, and which is very much necessary for decoding of the signals appropriately. Thank you.